I have the pleasure to present the work for the modeling of ductile fracture using a micromechanically motivated model. And that has been carried out together with Associate Professor Morin and Professor Sture Hopperstad from my research group at NTNU in Trondheim. So modeling of ductile fracture in metals is typically carried out using either porous plasticity or using metal plasticity and some damage model. There are different, we have several of these models, like the modified Mohr-Coulomb, Horsford-Coulomb, Liu, and Hu. But common for all of these is that they involve a lot of different parameters, and therefore also a lot of experiments are necessary for a proper calibration. Furthermore, they also require a damage accumulation rule, like in the integral to the right of the screen, which holds for proportional loading. But in real life, we typically see non-proportional or at least slightly non-proportional loading, like indicated in the line plots in the lower right corner. So in this presentation or in this work, we wanted to look into the crack initiation points and crack propagation paths in different test specimens. And to do so, we're applying the following methodology. First of all, we're using strain localization analysis to obtain the fracture strains for different stress states. We consider a homogeneously deformed material with an imperfection band in the center. The imperfection band is assigned porous plasticity parameters, while the rest of the body is assigned material metal plasticity. We load this body continuously while requiring continuing equilibrium and continuity across the imperfection band. And then as soon as the localization condition, the determinant of the acoustic tensor equals 0, as that condition is fulfilled, we store the equivalent plastic strain as the failure strain, as indicated in the surface plot to the right. And then we're using these points to calibrate a material fracture model, which we implement in simulation software and run simulations using different test specimens to study the crack initiation and crack propagation. So to illustrate this methodology, we are using an aluminum alloy, the 6000 series. We're applying extended water work hardening rule and a Hershey yield surface with exponent of 8. And to calibrate the strain localization model, we're using one single uniaxial tension test. We're setting up a simulation model of this test, extracting the deformation gradient history from a critical point in this simulation, and then we feed this one to the strain localization analysis model. Then we adjust the nucleation rates and the initial void volume fraction to make sure that the strain localization model provides failure or predicts failure for approximately the same strain as seen in the experiments. After that, we assume that the strain localization model provides correct results also for an arbitrary proportional loading for different stress structuralities T and loader parameters L. And then we create a point cloud like in the lower right corner, and we can fit a material model or a fracture model using using these points. And that leads to the question, how does this fracture model look like? Because in the literature, there are numerous of these models. But what we wanted was a model that follows this the data from the strain localization model as seen in the surface plot to the left closely, and that it does not rely on a damage accumulation rule. So what we see from the surface plot is that it's decreasing monotonically along the stress structurality direction. It's shaped like a half pipe, and it's slightly tilted. So the first term in the equation, labeled growth, is there to ensure the monotonic decrease. The second term, labeled shear, is there to ensure the half pipe shape. And the third term, labeled distortion, is there to mimic the tilting of the surface. Then again, we also see that this expression is the rate of the damage, d dot, which means that the damage itself can be obtained by means of integration. And that is also utilized when making a locus form of this rate form. So by starting from the rate form on the top, we integrate the expression for the damage from the initial damage to the critical damage. And we, for proportional loading, that's important. And then we can obtain the locus form. But then again, we need a damage accumulation rule, like in the integral, to the right in the locus form box. And we use the same linear one as previously discussed. But before we can apply this model, we need to calibrate it. And that is done during or through 5 different steps. The first step is to decide upon the initial damage, d naught, and the critical damage, dc. Even though they're not, even though they don't really have a direct physical meaning, we want to choose them such that they have a reasonable values as if they were void volume fractions. Next step is to look at the generalized compression. Then we calibrate kg and the psi parameters in model. We fix them and continue to the generalized tension, where we calibrate the kd parameter. From generalized shear, we get the ks parameter, and at last we get the alpha parameter, which controls the shape of the half pipe for all of the data available. And the data that we're using for calibrating, that's the data from the strain localization analysis. And the surface plot to the right shows the this corresponding data, but obtained from the calibrated model. And what we can see from the line plots in the upper right corner is that that is the data as drawn line from the model, and plus icons from the calibration data. And in the rightmost plot, we see that the blue line for a stress structurality of 0.2, the data is quite, the model is quite off, but that is also outside the calibration domain of the used for the model. But then with calibrated fraction model, we're continuing to the evaluation strategy. So for high stress structuralities, we're using test specimens, notch tension, notch test specimens and plane strain test specimens. We're also using the in-plane simple shear stress for low stress structurality, and Arkin for looking into in point of initiation and a crack path. And here we see some results using the rate form and the locus form. And as you can see, it does not fit that well with the experimental data. But the point here is that the locus form and the rate form provide very similar results. And to dive a bit more into the details, I will focus on the NT3, the ISS, and the Arkin 45 test specimens. This slide shows some results from the NT3 specimen. The contour plots to the left indicate the accumulated or the damage upon fracture from the locus form compared to the rate form. And we see that the rate form provides a much more narrow damaged area than the locus form. In the center top plot, we see the damage evolution for a critical element in using the locus formulation and the rate formulation. One important thing here is that they both indicate or they reach their critical value for the same global displacement, but the way to get there is quite different, where the locus form has a more steady increase, while the rate form is increasing a lot at the end. The line plots to the right indicate the stress state plotted along the global displacement, and we observe some non-proportionality, but still we get very similar results globally speaking, as shown in the center bottom plot. Similar results are obtained for the in-plane simple shear test specimen, with a much very narrow damaged area for the rate form compared to the locus form, and but still almost the same point of failure at approximately the same global displacement. And for the Arkin test, still the same effect with a more narrow damage distribution for the rate form compared to the locus form, and also the path and the point of initiation is very similar between the two variants. One thing to note here is that the locus form suggests that some areas might be critical or might become critical at later points, but the rate form does not indicate that at all. And to summarize, the choice of a locus form or the rate form does not have a significant impact on the crack initiation point or the crack path propagation, but choosing one rather than the other one might change how we perceive the damage zones. Thank you.